SwayamPrabha. Digital India. Educated India.
So, let us carry on diffusion, and before I talk about temperature dependence of diffusivity, just to let you know that there are another way of solving this diffusion equation, second law of Fick's, that is known as the semi-infinite medium. Suppose let us suppose a case, a limited amount of some diffusant is deposited at one end of a specimen, that is what is shown here, a limited amount at time t equal to 0. So, therefore, initial distribution is that at x equal to 0 or t equal to 0, there is a certain value of diffusant, and after that there is no more supply of the diffusant. Okay, it is only supplied once. This is also known as thin film configuration. So, what will happen if I then heat this specimen for a long time at something what is known as diffusion annealing. Slowly this diffusant will be diffusing into the sample. Then we can actually do the serial sectioning of that. We can cut small pieces like this, that is what is shown in the next picture, and then measure composition of that in each of these pieces. If I measure the composition and plot it as a function of depth, I should see a change like this. That means it will be very high at x equal to 0, and at a distance x equal to x it will be low. Okay, so, therefore, this allows us to actually calculate or measure the diffusivity D. Okay, so, this is known as tensor diffusion. This kind of situation arises in many cases. The one example is the semiconductor doping. Okay, suppose we have a silicon here, and this is silicon dioxide on the surface, and you want to dope this region of silicon with some boron or some, let us say, phosphorus or whatever. We just put a gas, and this gas will simply allow this dopant to be diffusing into this. Okay. So, once a certain depth to which it diffuses, the dopant gas is stopped. Actually, specifically speaking, initially it is exposed to the gas and the gas is stopped, and then it will be slowly diffusing inside the surface, and finally an Si2 layer is built up. So, the first process is known as P deposition, that is why you control the dose, and second one is known as diffusion or drive-in. Okay. So, P deposition by diffusion can also be replaced by shallow implantation. That means you can implant boron or phosphorus. Normally boron can be implanted very nice easily. So, you can implant to a certain depth and then stop it. Then you can actually allow the things to diffuse, or you can do the diffusion annealing. So, this kind of situation arises in the real life, and this is nothing but a semi-infinite medium. So, semi-infinite medium do exist in the actual practice, and that is why we need to this is experimental, but we can actually solve the equation and get the values. Okay, so, in all this, remember one thing, we have assumed D is independent of time, temperature, sorry, but D is never independent of temperature. When we are doing the diffusion annealing, we are assuming D is independent of temperature, but that is not the case, and that actually changes the diffusivity. So, how we can deal with that? Let us go back to our earlier lectures, how the diffusion happens in a substitutional solution. Let us suppose there is a vacant site and an substitutional atom is diffusing from one position to other position. If it diffuses one position to other position, what will happen? This will push the atoms which is present at these positions, and this pushing will lead to certain kind of a work done by the system. So, that means what? From A position to B positions, the atom if the atom needs to go, it will has to cross over a barrier, and that barrier is nothing but a migration barrier. That is why it is written GM, and this migration barrier needs to be bypassed, or needs to be rather crossed by the atom to reach from equilibrium position here in this position to this position. That is what is shown here. So, this has to be a thermally driven process. If temperature is not, temperature means thermal sufficient energy is not provided, the atom at the central position here cannot move to the next position, or rather diffusion cannot happen. This is why actually the diffusivity must be dependent on temperature. So, simple analogy tells you that. Now, how can we actually make it very clear? This is why actually I have taken some slides from the internet, and I am explaining in a more detailed manner. 3 different configurations are shown nicely here. Let us suppose this is the configuration where one atom is sitting there, solid atom is little bigger size, and this atom has to move from here to there. So, if it has to move, it will first land up there, that is what is shown in the second step, then finally from there it will go. So, there is a barrier, that is very clear, we need to explain more further. Now, in an interstitial case the same thing will happen. Interstitial atom suppose going from here to there. So, from here to here if it goes, it will again push these 2 atoms, then reach here, again reach here, again from here to there it will push these 2 atoms, again that, okay. Similarly here, here. So, every time it has to pass from one interstitial position to another interstitial position, the atom will pass through a barrier. So, that means system needs to do some work, okay. And this, remember, atoms in a finite medium at a certain temperature T, they are vibrating, or they are actually colliding each other, and they are vibrating with certain frequency. Let us suppose this vibration frequency is equal to nu, right. So, that means what? Every time atom is making an attempt to cross this barrier, very simple, it will just make an atom jump to cross this barrier. So, as this barrier height, here it is E, let us write G, G is better, this barrier height is GM. So, the probability of the number of atoms which have sufficient energy to cross over this barrier will be this, because that is obviously exponential term, and it will be G by RT, because your RT or R is for 1 mole and K is for a single atom. So, Gm by RT or Gm by KT is nothing but energy available to the atom to cross the barrier. So, RT is the thermal energy and Gm is the barrier height. So, therefore, the fraction of that energy is what is the probability that atom will cross over this barrier, right. So, now obviously it has a frequency, that means it is doing, the atom is doing attempts, certain number of atoms per second, and this is given by nu. So, nu into exponential minus Gm by RT is what is giving us a total number of jumps, successful jumps which it can take to cross over this barrier. So, that is possibly for one position, but it might be there are many positions available, many vacant positions available. So, it will try even not only for one sides, it can try even this side, this side, this side, like here. When the interstitial atom is moving, it can move this way, it can move this way, it can move this way, it can move that way. So, depending on whichever directions it can, its availability of these free sides, free positions, it can do that. So, let us suppose that is what is the Z. If the Z is number of sides available. So, this is tells you, this is what is tells you the diffusivity, nothing but diffusivity. But remember, this is not the actual diffusivity. In a 3 dimensional, this must be equal to 1 by 6 alpha square, or A square, okay. The A is the distance I have written here, A is the distance written there, I am sorry. So, A square, correct. That comes basically when you assume that there are 3 x, y, z directions, because this is done in 1D. So, in 3D there are 3 directions. So, there are 6 different directions it can do, plus x, minus x, plus y, plus z, minus x. That is why it is divided by 1 by 6, and A is the distance. So, therefore, the diffusivity has to be square of distance, that is why A is put it there. and nu is basically frequency, that is per second or per hertz. So, that is why exponential term has no units, that is why it is there. So, now we can actually write down this as very simple equation, very simple you can write down that, I am sorry it goes back, is z nu a square exponential minus gm by RT, right. So, that is nothing but 1 by 6 z nu a square exponential s m by RT, because gm is nothing but hm minus TSM. This is any P energy migration or does not matter, this must be equal to H minus Ts. So, therefore, if I can take out the SM term is the entropy. So, there is a minus sign, the minus will become plus. I can write down this as like this, minus Hm by T. So, first term is always considered to be constant. Why? At a temperature T, remember that. Sorry, the T will vanish. Why T will be here? Because we have already taken RT, say Sm by R. So, as you know, Z, number of vacant sites available to which the atom can diffuse, is also constant. Nu is the frequency of vibration, that is also constant. A is the distance between two lattice sites, that is a constant, and Sm by R is also constant. Sm is the entropy of migration, R is universal gas constant. That is why this is whole thing is a constant. Only thing is here is exponential minus Hm by RT is not a constant as a temperature. So, if I go back on the next slide, so I can write down D is nothing but a constant term G0 exponential minus Hm by RT, and that is what is written here. Hm is replaced by Qd. Heat Hm is nothing but enthalpy of migration, that is nothing but the activation energy for migrating one atom from one site to the other site. So, that is why you see this fundamental equation always, D is equal to D0 exponential minus Q by RT, where Q is nothing but activation energy for the diffusion happen, and R is a constant universal gas and T is a temperature. So, and temperature must be in absolute scale, temperature is never considered as a normal Celsius, or it has to be in Kelvin, and R is constant, it is known as 8.314 joule per mole Kelvin. So, simply we can actually calculate D at any temperature, provided we know the Qt, and this we will discuss about Qt more maybe in next 5 minutes time, but please remember this is again in diffusion is a very fundamental equation. This directly derived from the assumption that diffusion of atom requires some activation barrier to be crossed. So, depending on the type of diffusion, there is a substantial atom diffusing, or it is interstitial atom diffusing, or a vacancy diffusing. As I mentioned in the first lecture, the vacancy can also diffuse. The atomic motion can be considered to be a vacancy moving. Depending on which are the pieces, or which is the type of diffusing pieces, this Qd is going to be different. Obviously, for interstitial atom, Z is very large. So, therefore, D0 is very large, and activation energy for the Q is also low, because there the interstitial atomic size is so small, the amount of pushing required by the atoms to move from one position to other position is also very low. That is why the interstitial atom diffuses faster. That is why carbon, nitrogen, oxygen, they diffuse faster in steel, not iron, not manganese, not the other substitution elements. This is the main reason. Remember, D0 does not change much, D0 is a P exponential term, it is always assumed to be constant. It is the Q which actually dictates the value of D at any temperature, and Q depends on type of diffusion mechanisms we are seeing in the literature. So, that is the very important aspect, please remember. Now, I can actually get, okay, let me just write down expression again and explain to you. So, we have write down D equal to D0 exponential minus Qd by RT. it is always important to measure QD, because QD tells you what is the kind of diffusion mechanism taking place in a material. To do that, we can actually simply take a log on both sides. We can write down log of d or log of d0 minus 2.303, oops, sorry, not 2.203, it is q by RT, right. This log here is ln. So now actually I can always make a plot of log of d versus 1 by t. What I should get? I should get a straight line with a negative slope, and slope of this curve is basically q by r, this slope, and intercept is minus log of d0. This is straight line equation, y is equal to mx is this plus c. So therefore, if I measure d at different temperatures, d means capital this d1, d at different temperature, and plot log of d as a function of 1 by t, I should be able to measure the q. And this q is very important. The q tells you what kind of diffusion mechanism is prevalent in a particular material, and that is why q needs to be measured always. Here actually I am plotting d as a function of 1 by t, but it is not 1 by t, 1000 multiplied by 1 by t, because that makes the numbers easily understandable. And the top axis you see temperatures as shown, exact temperatures. What you see here? Carbon in gamma iron, carbon in alpha iron. Let us first look at these two. You see the slopes of carbon in gamma iron is very high, steep slope. The higher the slopes, higher is the value of d. Okay, that is why you see here d is something like 10 to the minus 8, 10 to the minus 9. Carbon in alpha iron is also very high, but slope is slanted. So that means what? The barrier for diffusion of carbon in gamma iron is much lower than carbon in alpha iron. That is obviously gamma iron is FCC structure, number of octahedral or tetrahedral voids, and their sizes are different than in alpha iron, and that makes the carbon diffusion in gamma iron much easy. That is why in steel metallurgy we always hit the sample to the gamma phase, because we want carbon to diffuse uniformly. This is the reason, main reason for that. Now if you look at iron diffusion in compared to that, iron is a solid, iron is a substitutional element. So iron in gamma iron and iron in alpha iron, they are having same slopes, but they are much lower, 10 to the power minus 9 and 10 to the minus 14. It is almost 3 orders of magnitude or 4 orders of magnitude lower value as compared to carbon at any temperature. That is the reason why substitutional things diffuses very slowly, and that is basically QD is very high, and as the QD increases it is a negative, so therefore exponential term decreases, and that is why the diffusivity decreases. Aluminium is even much difficult, more difficult. Why? Because its slope is still lower. Because aluminium is a self diffusion, and self diffusion is more difficult. Iron in alpha iron is not a self diffusion. You have already carbon, manganese, and so many things are there. So therefore we cannot call it a self diffusion. Okay, so that is the taken from Callister. So that is very simple way to explain you how the values actually is there in the actual literature and how d depends on time. Let us give an example, mathematical example. At 300 degrees Celsius temperature, diffusion coefficient and activation energy of copper in silicon are actually given by these. 7d is basically 7.8 into the minus 11 meters per second, and the activation energy is QD is basically 41.5 kilojoule per mole. So what is the diffusion coefficient at 350 degrees Celsius temperature? We need to know the many things. So what do we have? We have a d versus temperature, we need to transform into d versus 1 by t. Okay. So log of ln of d2 is basically ln of d0 minus qt by q by rt. That is the equation I have already shown, and we can always write down d1 is like that. So at t1 we know the d1, so we can measure easily d0, okay, and also we can measure d0 because q is given already to us. So as you clearly see that you can do the maths very easily. Temperatures must be converted, and d2 is basically 70.8 10 to the minus 11 multiplied by these terms. Okay, this is QD, this is R, and this is the temperature differences. So what do you get? It is basically 15.7 to the minus 11 meters per second. That is what you get. Okay, so very simple. We are actually applying this exact equation. D2 is known, D1 is known, QD is known, D1 is known, not D2 is known, QD is known, T1 and T2 are known. Therefore, D2 is nothing but calculation of the exponential term. Well, we can actually show even much many data. You see hydrogen in FCC-Rn is very high because it is interstitial 10 to the power minus 4. Remember this is very high value. Carbon is 10 to this is centimeter square per second, therefore in meter square it will be 10 to the power minus 4 has to be multiplied, so 10 to the minus 7, 10 to the minus 6 will be 10 to the minus 10. And you see Rn in iron oxide is also very high because all this is substitutional, but still because there is open spaces available. But Rn in FCC-Rn, Rn in BCC-Rn is pretty low. Magnesium in magnesia and calcium in calcia is very very low. Look at here one important aspect, the carbon in graphite, cell diffusion. Carbon in graphite is extremely slow because graphite has very less number of sites available. Vacancies are very low in graphite normally because high melting temperature material, so therefore vacancy concentration is very low. Carbon melts at 3600 Celsius temperature, therefore at a temperature of something like how much? Something like 1000, 2000 degrees Celsius temperature, number of vacancies is very low. So therefore carbon will, where the carbon will diffuse, cell diffusion is that's why is very low. That's why actually graphite is used in all kinds of high temperature applications because diffusion is slow, graphite will not get affected. That is another reason I just wanted to show you. Okay, so just to give an idea before I wind up, cell diffusion is always very slow and cell diffusion is always happens. Let us consider copper wires. Copper wire is basically virtually very pure copper with a very little amount of oxygen, that is why it is called oxygen free copper, which is used in the all the wirings. Now once the electricity flow inside the copper wire, because of Joule effect temperature will rise. Temperature rise may not be very high, but it will rise, depends on the value of the current. So because of that diffusion of copper will happen, copper atoms will diffuse through the copper lattice itself, and that is what is known as cell diffusion. Remember this is very slow, but this is not negligibly small. So cell diffusion is a diffusion of an atom to a new site in its crystal where all atoms are same type. That is what iron in iron, aluminum in aluminum. Here I am showing copper. Suppose there is some kind of a atom here and some kind of vacant side here. So therefore the vacancy is moved, atom will move this side, and we can have many different mechanisms. So therefore the QD value for cell diffusion is always very high. That is why the cell diffusivities are pretty low. So with that let me wind up the diffusion, and the next lecture we are going to talk about interfaces. Interfaces means what are different type of interfaces, how do interfaces play a role in dictating different aspects of phase transformations, and subsequent to that we will start actually phase transformations, different type of phase transformations. Okay.